Dear students, let us start with the third unit of your course, that is the differentiability of functions. So from your higher secondary classes also you have done something about differentiability, and you know some geometrical concepts of or say now geometrical meaning of differentiation, okay, of dy dx, okay, this symbol that we write. Okay, so some of the concepts were there. Let us just try to recall a few. Suppose you have a function of this type, right, and you want to find out the derivative of this function at some point, say c. Okay, so which is a point here, right? C is a point in this part, and of course this point is c comma f of c. And this point is c comma f of c, and the given function is say y equal to f of x. Okay. So what we do is actually we try to analyze the this ratio. Okay, we try to analyze this ratio fx minus f of c divided by x minus c. Okay, so what is that ratio actually? As you know, if we take a neighboring point here, right, say at any point x, and we draw this triangle here, so this particular distance or this particular height is actually your fx minus fc or fc minus fx. Okay, and this distance is your c minus x. Okay, as part of this diagram it's c minus x. If x is on the other side, it will be x minus c. So in any case, the that is distance is modulus of that. Okay. So this this ratio fc minus fx and c minus x, if we take this ratio, this actually gives us the angle tangent of the angle between these two, right? Tangent of the angle made by the line joining these 2 points, this x comma fx and c comma fc, okay, and the positive direction of x-axis. Okay, so this angle, right, tan of this angle is fc minus fx divided by c minus x. Okay, so as the point x approaches the point c, so what happens to this line is, say if x comes closer to c, so there is a tendency that this particular tangent the chord joining these 2 points, right, shifts in this direction. Okay, if you go further close, okay, the point the chord may become something like this. Okay, and that way, if you keep on going, if it is something like this, and in the limiting case, if that actually coincides with the slope of the tangent at this particular point, okay, at this point, suppose we draw a tangent to the curve, so at some particular if the limiting value of this fraction becomes equal to the slope of the tangent at the point c, okay, then we say that this function is differentiable at the point c. Okay, and this particular fraction is denoted as f dash c. So this is nothing but the limiting value of x tends to c, fx minus fc divided by x minus c. Okay, so it actually measures the rate of change of f with respect to the rate of change with respect to the change in x. Okay, so that is the basic geometrical idea. So how do we define this? We define it this way: differentiability of a function. Differentiability of a function at point. So we will, for the theoretical purpose, we'll consider differentiability means the domains of the functions as intervals. Okay. So of course other domains can also be taken, but we have to make sure that the point where we are testing the differentiability has to be a limit point of the domain. Okay. So yeah, so this is the concept. Let I be an interval. So it might be closed interval, it might be open interval. That's not a problem. Let I be an interval, and f I subset of R. Okay. We are dealing with real numbers only. So I'll let I subset of R be an interval, and f is a function from I to R. Okay, and let C belongs to I, be any point. Be a point. Right? Then f is differentiable at C if there exist, say some what should I say, some L belongs to all L, or say alpha. There exists an alpha in real number such that given any epsilon greater than 0, there exists a delta greater than 0, such that mod of fx minus f of c divided by x minus c minus alpha. Okay, means this function fx minus fc by fx minus c has limit alpha, okay, at c. That is the meaning. So this quantity can be made less than epsilon for all x in I satisfying mod of x minus c less than delta. Okay. So this is basically the definition of limit of fx minus fc divided by x minus c. So in other words, limit x tends to c, f of x minus f of c divided by x minus c exists. Okay, if it exists finitely, then we say that its function is differentiable. There is a finite real number which is the limit of this ratio. Okay, then f is said to be differentiable at c, and we will say that f is differentiable in I if it is differentiable at every point of I. Right. So if f is differentiable at every point of I, okay, then f is differentiable in the interval I. Okay, right. So for example, let us try to see some examples where the function is differentiable. So let f from let us take it from R to R itself, defined by say fx equal to twice x. Okay, then f is differentiable at any point c inside R. Okay, so how to check that? We will try to see whether this limit exists or not. Okay, so we check the limit limit x tends to c fx minus f of c divided by x minus c. So this is same as limit x tends to c of fx is twice x and f of c is twice c divided by x minus c. So by our properties of evaluating limits, it's something like 2 into x minus c divided by x minus c. So that comes out to be equal to 2. Okay, so this exists finitely. Therefore, your f dash c is actually equal to 2. Okay, so this is how we evaluate the limits. Sorry, evaluate the derivative of a function at a particular point c. Okay. So another way of writing the derivative is this. If I want to find out the derivative at a particular point x, okay, at an arbitrary point x, right? Since usually we have some functions denoted as f of x equal to some expression of x, and we need to find out what is f dash at such an arbitrary point. Okay, so in that case, what we do is we just evaluate this limit h tends to 0, f of x plus h. So any point x in the neighborhood of any point in the neighborhood of x can be written as x plus h, where h may be positive or negative. If h is positive, then x is in the right side of and if h is negative, then it is in the x plus h is in the left side. Okay, so no matter where it is, any point in the neighborhood of x can be written as x plus h. So it's f of x plus h minus fx divided by h. We try to evaluate this limit, right? So this if this limit evaluates as a finite quantity, which is a function of, which will be some function of x, okay, then we said that this function is differentiable, and this expression gx is actually denoted as f dash of x. Okay, say something like evaluate f dash x, where f of x is given by, say, x squared. X belongs to R. Okay, so the domain of this function is R. I want to evaluate f dash x. Okay, so we evaluate limit h tends to 0 of f of x plus h minus fx divided by h. So this is equal to limit h tends to 0 of x plus h whole square minus x square divided by h. So this is limit h tends to 0 of, so x square plus twice x h plus h square minus x square, so divided by h. X square cancels from the last and first expression, so this is equal to limit of h tends to 0 of twice x h plus h square divided by h. So if we just simplify, this comes out to be twice x. Okay, so the derivative of f at any point x is given by twice x. Okay, so we write this expression as dx of x square is equal to twice x. Okay, so this is one way of evaluating the derivative. So of course you have done these things in your higher secondary classes as well. So one important property that you have also learned in your higher secondary classes is this: every differentiable function is continuous, or differentiability implies continuity. Every differentiable function is continuous. Okay, or differentiability implies continuity. In short, we also write it this way: differentiability implies continuity. Okay, and in a proper way we write it something like this: let f from I to R be differentiable at C belongs to I, then f is continuous at C. Okay. So how will you prove it? So we prove it using the definition of this continuity and differentiability. So f is continuous at C means what? Limit of, you have to show limit x tends to C f x, this is equal to f of C. Okay, so remember we are concerned about differentiability and continuity of functions in an interval. Okay. So always this type of limit concept is applicable. Okay, so what we need to do is we need to find out the limiting value of this fx and minus fc. Okay. So we have fx minus fc, f of c, we have fx minus f of c. This can be written as fx minus f of c divided by x minus c into x minus c. Okay, for whenever x is not equal to c, right? So for all x in I, x not equal to c. Okay. So from here you see that it is already given that f is differentiable. That means this limit, if we take the limit of this part, this limit is a finite quantity, it exists. Okay, and already this limit also exists. Well, limit of x tends to c of x minus c, this limit is nothing but 0. Okay, so if we take limit on both sides, limit of this function, this will be equal to limit of this product, and since each of the individual limits exist, so the limit of the product can be separated. Okay, we can distribute the limit of the product and it will be equal to the product of the limits. Okay, so taking limits, we see that limit x tends to c of fx minus f of c, this will be equal to limit of x tends to c of this product fx minus f of c divided by x minus c, then multiplied with x minus c. Okay, so this is the limit of the product, right? Now we will use the fact that now f is differentiable at c, so this limit x tends to c of fx minus f of c divided by x minus c exists. Okay, exists finitely. So let f limit x tends to c of fx minus f of c divided by x minus c is equal to, say, f dash c, right? Also limit of x tends to c of x minus c, this also exists, is equal to 0. So the limit of product in the right hand side can be reduced to a product of limits. Okay, right? So thus we have, therefore, limit x tends to c of fx minus f of c, this can be written as limit x tends to c of fx minus fc divided by x minus c multiplied with limit x tends to c of x minus c. Okay, so limit of the product is equal to product of the limits. So this is nothing but f dash c, and this part is nothing but 0, so this is equal to 0. So this implies, so here also in the left side also I can separate by the properties of algebra of limits. Limit x tends to c of fx, so this particular limit exists, so the individual limits also exist. Limit of x tends to c of fx is equal to so here this is a constant, fc is a constant, so this limit exists and the whole limit exists, so this limit also has to exist. Okay, that also follows by algebra of limits. So limit x tends to c of fx is same as f of c. So, and this means that f is continuous at c. Okay, so differentiability implies continuity. Whenever f is differentiable at a point c, it is continuous at c. Okay, but the converse is not true. Continuity may not imply differentiability. Okay, so one famous example that all of you might know, fx equal to mod x, say x belongs to R, is continuous at 0, continuous at x equal to 0, but not differentiable at 0. Differentiable at 0. Okay, so how to show this? Fx is continuous, no doubt. Mod of fx equal to mod x. If we take mod of f of x minus f of 0. Okay, so let epsilon greater than 0 be given. Then this will be equal to mod x minus 0. Okay, so it's mod of mod x, so it's something like mod of x minus 0, and this can be made less than epsilon whenever mod of x minus 0 is less than delta, where delta is just epsilon. Okay, if we take the difference between x and 0 less than epsilon itself, then the difference between fx and f0 is also less than epsilon. Okay, so therefore f is continuous at x equal to 0. Okay, so this is a simple exercise from the earlier units. But now I have to show that f is not differentiable, right? So let us evaluate limit. I have to evaluate it's not differentiable at x equal to 0. So let us try to evaluate limit x tends to 0 fx minus f0 divided by x minus 0. So this limit is actually limit x tends to 0 of, what is fx? Fx is mod x, f0 is 0 divided by x. Okay, so this is limit x tends to 0 of mod x by x, right? So this so this limit doesn't exist. Why it doesn't exist? So there are several ways of showing this. You can in fact show it using this left hand limit, right hand limit concept, so which doesn't exist as limit x tends to 0 plus of mod x by x. If we approach 0 from the right side, in that case mod x is just replaced by x, so it's 1. But if we approach from the left side, x tends to 0 minus of mod x by x, this is actually limit x tends to 0 minus of mod x will be minus x in that case, so minus x by x, so that is minus 1. Okay, so mod x is an example of a function which is continuous at x equal to 0 but not differentiable at x equal to 0, right? Okay, similarly you can have this type of function, say x minus 1. This is continuous at x equal to 1 but not differentiable. not differentiable. Okay, so it's quite easy, you can try it. So if you have some question like give example of a function, example of a function that is not differentiable at exactly, that is not differentiable at exactly, say 3 points. Okay, so the simplest way that you can answer is this is fx equal to mod of x plus mod of x minus 1 plus mod of x minus 2. Okay, so this function is not differentiable at x equal to 0, it's not differentiable at x equal to 1, okay, and it's not differentiable at x equal to 2 also. Okay, so this is one simple example. So immediately using this concept itself, we can give examples of a function that is not differentiable at exactly say 1000 points. Okay, so we can just take the sum of this moduli, right? Say another example, let's say something like give example of a function that is twice differentiable but not 3 times. Twice differentiable, so after differentiating once I can also again differentiate once. So twice differentiable but not 3 times, but not thrice. Okay, so that example also, it's just inspired by mod x. You take fx as the function, they say something like x cube when x is greater than or equal to 0 and minus x cube when x is less than 0. Okay, so if you see, if you can find out what is f dash of 0, f dash of 0 is limit x tends to 0 of x cube minus 0 cube, okay, divided by x minus 0. So this is nothing but limit x tends to 0 of x squared, so that is 0, right? So the first derivative exists. F double dash 0, how do you find it out? Okay, so for that actually we need to find out what is f dash x at other points. So at other points, you already know when x is not greater than 0, the derivative of this x cube is 3x squared. Okay, so this will be 3x squared when x is greater than or equal to 0 and minus 3x squared when x is less than 0. Okay, so f double dash, that means I have to find out the derivative of this. This will be limit x tends to 0 of 3x square minus 0 divided by x minus 0. So that is nothing but again 0, 3x, because I'll get something like limit x tends to 0 of 3x. That is 0. So it's twice differentiable. Okay, now let's see. Yeah, so it's twice differentiable, but third time is it differentiable or not? So f dash we have found out, f double dash will be, so for the other values it is like 6x when x is greater than or equal to 0 minus 6x if x is less than 0. Okay, so if you observe this function carefully, you will see that it's not 3 times differentiable at x equal to 0. F triple dash 0, if we say something like this, then limit x tends to 0 of f double dash x minus f double dash 0 divided by x minus 0. So this is what limit x tends to 0 of 6x minus 0 divided by x minus 0. Okay, when x tends to, yeah. So for the earlier case, you see what was the result? Okay, I did it directly. There was some mistake actually. Limit x tends to, we had to evaluate it in 2 steps. Okay. F dash 0, this I have to write it in 2 steps because the definition of the function is different when the approach towards 0 is different. Okay, So I need something like limit extends to 0 plus of this fx minus f0 by x minus 0, so that is 0. And also I need to evaluate limit extends to 0 minus. 0 minus will be minus x cube minus 0 divided by x minus 0. So in that case also it is 0. So here also we need to evaluate this limit extends to 0 plus and limit extends to 0 minus. Okay, so please correct that. We have to evaluate both of these two because the definitions are different, right? So here also I have to evaluate, instead of writing f triple dash directly, let us try to evaluate limit extends to 0 plus of this. So this comes out to be 6. But if you evaluate limit extends to 0 minus of f double dash x minus f double dash 0 divided by x minus 0, so this will be equal to limit extends to 0 minus of, so in the 0 minus side it is defined as minus 6x minus 0 divided by x. So there is actually minus 6. So that means this function f triple dash 0, this doesn't exist. So this is an example of a function which is differentiable twice at a point, but not 3 times. Okay. So using such examples, you can also construct functions which are 3 times differentiable at a point, but not 4 times. Okay, so just you take x to the power 4 and minus x to the power 4. Okay, so that will work. You can also find functions which are differentiable 100 times, but not the 101th time. So that way also you can think of. So this is a very powerful example that we have taken, right? If you take x cube minus x cube, it will be twice differentiable but not thrice. If you take x to the power 4 minus x to the power 4, it will be 3 times differentiable but not 5th time differentiable. Okay, like that. So one thing you observe that differentiability implies continuity. So if we talk of the contrapositive statement, we can say that not continuity implies not differentiability. Okay, so if a function is discontinuous at a point C, then we can safely say that it is not differentiable at the point C. Okay, so if f is discontinuous at C, then f is not differentiable at C. Okay, if it is discontinuous, then directly we can say that it's not differentiable at C. Okay, right? Say for example this function fx equal to greatest integer function of x in the interval, say x belongs to 0, 3. So this function is discontinuous at the points 1, 2. Okay, at the points 1 and 2. So at those 2 points the function cannot be differentiable, right? Okay, so this is the greatest integer function, greatest integer less than or equal to x. Okay, so let us see some other examples. Let's say if f of x is, say, sin x, how do you evaluate what is f dash x? Okay. So for that, what you have to do is you have to find out this ratio, limit h tends to 0 of sine of x plus h minus sin x, right, divided by h. Okay, and after that you have to use some sort of trigonometry, sine of c minus sine of d, this type of formula. Okay, so it's sine 2 cos c plus d by 2, I think, right, twice x plus h by 2 into sine of c minus d by 2, that is h by 2 divided by h. Okay, so one result that we can use is limit of h x tends to 0 sin x by x, that is always 1. So this 2 I can take it down there. So sine of h by 2 by h by 2, that is always 1, and this limit exists. If you tend h to 0, this limit will exist and it will be equal to cos x. So derivative of sine x is same as cos x. Okay, so that way, so in your higher secondary you have done lots of such examples where you calculated the derivatives. Okay, so please try to practice some of these also.